Hi everyone. Today what we're going to be looking at is how do we predict products of a reaction if we're only given the reactants. As you can imagine, that's a really useful skill for a chemist to have. I want to know when I put two chemicals together, what are they going to do? I don't like being surprised. And when I put two chemicals together, I need to know if I'm trying to get something specific, if I put these chemicals that's what I'm going to get. So the first thing we need to be able to do is to identify the type of reaction at hand. Now you'll notice that I only have 4 reactions sitting here when we really have 6 reaction types. Well, the reason for that is none of these are going to be synthesis reactions and none of them are going to be decomposition reactions. Those 2 types don't always do exactly what we expect them to do. One substance can fall apart in 2 or 3 different ways, could decompose into different options, and you wouldn't have a rhyme or reason to know which way it is, so I would never ask you to do that. So what we have are our 4 reaction types minus the synthesis and the decomposition. So we're going to do them one at a time so you can see the patterns that go along with each of those. So I'm going to zoom in here a little bit. Okay, we'll move the first one down into place. So this first reaction that we've got, okay, we take a hydrogen compound and a compound with a hydroxide on it. Okay, so we found before that compounds that start with a hydrogen are generally acids, and things that end in hydroxide, those are bases. So this we already know is going to be an acid base reaction. So let's look at what our products are going to be. We know that acid-base reactions always make water. Okay. Plus, the other compound is going to be the 2 ions that are left, because the water is made out of the hydrogen and hydroxide. So the 2 ions that are left are going to produce that final compound. So we're going to name it first. Okay, the name of that compound, because I know I put the positive ion first, is calcium chloride. Okay. So then we're going to look at the compound that you would get if you had the name calcium chloride. Remember, this is going to be an ionic compound, so we're going to have a Ca2 plus and a Cl minus, which means that my final formula is going to be CaCl2, right? Because this 2 is going to cross down there. Now, what phase labels are these things going to have? Well, we know that water is going to be a liquid unless there's a lot of heat hanging around, which there isn't here. And my calcium chloride, I'm going to tell you, these are always going to be aqueous. When I have an acid-base reaction, I always end up with liquid water in an aqueous ionic compound. Okay, so I'm even going to write that. Products are always liquid water aqueous ionic compound. Okay, so our next reaction here, I have a lot of carbon and hydrogen reacting with oxygen gas. Well, we know that react with oxygen gas means to burn, and if it's a carbon and hydrogen compound, means this here is going to be a combustion reaction. Well, combustion is about the easiest one we've got. The products of the combustion reaction are absolutely always carbon dioxide and water. So what are my phase labels? Well, I'm burning something, right? It's hot. Have you ever seen fire give off anything besides gases? I know that sometimes we end up with ash, but this is more like burning a candle, or I guess you got some soot, or burning natural gas or a propane torch, where it just kind of burns and whatever was in there, it seems to disappear because we get carbon dioxide gas and water that's still a gas. So our products are always, and you don't even have to think through these, if it's a combustion reaction, they are absolutely always carbon dioxide gas lost myself there. Okay, and water vapor. Okay, the next two get a little bit trickier. So this next one right here, I take one ionic compound plus another ionic compound, and neither of them are acids, and they're not an acid and a base. I just have two ionic compounds, which is going to make this reaction double displacement. Well, we've actually done double displacement reactions before. This is exactly what we did when we dealt with our precipitate lab. We took two compounds, our silver nitrate and calcium chloride, and we change around their ions. So instead of silver nitrate and calcium chloride, I get silver chloride and calcium nitrate. And edge the paper there. Okay, so then we look for those formulas. Silver chloride, silver is an Ag plus 1, and chloride is a Cl minus 1, so I don't end up with any extra numbers. Plus, calcium is a Ca, remember it's got a 2 plus, and nitrate is an NO3, and that 2 is going to come down here to my nitrate. So what are my phase labels? Well, I have no rhyme or reason to know right now, and I'm actually going to show you that in the next video. Okay, so we're going to have to decide what those phase labels are here a little bit. We're going to skip that one. Okay, oh, hold still. Products will be two different ionic compounds. Now watch your formulas. I want to point something out here. There was a 2 in the calcium over here, but chlorine, excuse me, there was a 2 in the chlorine right here, but I don't have one right here. Well, the reason for that is that this 2 came from our calcium ion. Well, the chlorine isn't with the calcium ion anymore, so it doesn't get that 2. It gets whatever the silver had. But the nitrate now only didn't have a subscript over here, but it does get one over here because, again, it comes from the calcium ion. You have to watch the formulas. You can't just automatically assume that these little subscripts carry along with the ions that they are on. They have nothing to do with the ion that they're sitting on. They have to do with the other ion. So keep an eye on that. Okay, so this last one. Process of elimination here. So most of you got this figured out. It must be a single displacement. I have an element. I have a compound. And so I'm probably going to make this be a single displacement reaction. So I'm going to abbreviate because I'm shorten it a little bit. So the way a single displacement reaction works is that this element is going to come in and kick out that element. So I am going to take the element that's in the compound and bring it to the outside. And I'm going to tell you right here that when I ask you to actually do these on any sort of assessment, it is always the metal that you're going to put in and out. I mean, we're going to take a metal here, put it in, metal here, and take it out. Well, I promise it will always be the metal. Okay. Plus, now we're going to insert the aluminum into that compound. But just like we've done before, we have to pay attention. So if I have aluminum sulfate, remember, aluminum had a 3 plus charge, so I'm going to need to bring that down to the sulfate. And my sulfate had a 2 minus, so I'm going to bring that down here to my aluminum. Okay, so what about phase labels here? This is copper, right? You've seen copper, and it's not copper as part of a compound, it is actually a piece of copper. Metals are solids, right? And then for the sake of simplicity, we are just going to always assume that this is now an aqueous solution, that we originally had a solid and aqueous solution. You're going to end up with another solid and an aqueous solution. So the products will always be a new metal and a new compound. So we take the metal that's by itself, it kicks the old metal out of the compound. The old metal is now sitting here all by itself, okay, and the new one, it becomes part of the compound. All right, good luck.